Hey, what's up? Mr. Mice is here again, and we are talking about interpreting rat graphs. Do you really want to look at rat graphs? Probably not. Calculus. We're gonna little cheeses, little cheese, big rats. We're gonna look at rate graphs. So graphs that are rates of change. So the graph initially is a rate. So instead of looking at maybe like the position and time graph, we're going to look at a velocity time graph and see what we can tell from that. So let's take a look at a graph here that I have. Something to note about rate graphs is that when we're talking about rate graphs, the graph itself, a point on that graph is itself a rate. So it represents a rate at a certain time. So like miles per hour, for instance. The slope of that is like the slope of a rate. That's the rate of a rate, right? So we're talking about a rate of change of the rate. So maybe like acceleration, miles per hour. So we're talking about the rate of a rate. Now, since we're starting at a rate graph, then we need to do an antiderivative to get back to the non-rate, or basically the accumulation of something that's happening. So if you could think about it as if it's velocity, if we go backwards, we're talking about the position, or in this case, the graph would be the accumulation of position, which would be the distance traveled, right? Or displacement if we're looking at the integral. So an integral kind of undoes the rate. It's like the undone rate. So let's think of it as if you take the area under the rate curve, we're accumulating. It's an accumulation of whatever we're talking about that was up here in the numerator of this rate. Okay, let's take a look at an example. I think that might make a bit more sense when I talk about it in context. So let's suppose I have this rate graph here, and this is the rate of rainfall in inches per hour. We're going to start at 0, so time in hours after midnight, which is important. So this is going to be, this is midnight right here. All right, so just label it as midnight. 0 is midnight. The graph at the right models the rate of rainfall inches per hour from midnight until 6 a.m. So we can see 6 a.m. is right here. Midnight is 0. And that's of a rainstorm. So let's go ahead and write a complete sentence that represents what the point A represents. All right, so we're looking at this point A. Now remember, the point A represents the rate of change of whatever we're talking about. So this is the rate of rainfall, at 3 a.m. So the rate, let's go and say at 3 a.m. At 3 a.m., what's happening? It is raining at a rate of 1 inch per hour. Okay, so again, that is the point. The point is the actual rate. So let's look at number 16. What is the slope of the graph between points A and B? So what's the slope of the graph between point A and B here? The slope of the graph, the graph that we're looking at is 0, right? So the slope of this graph is 0. So what does that represent when the slope of the graph is 0? That means the rate at which the rate of rainfall is changing is not changing, right? So it means that there's no change in rate. I know there's a lot of change. And every time I put the word change or rate or slope in a sentence, that's basically like a derivative. So I'm looking at the slope of the rate. So I'm going to say between 3 a.m. and 4 a.m. there is no change in what? There's no change in the rate of rainfall. Okay, you can also say that the rate of rainfall stays constant, all right, at about 1 inch per hour. Okay, I've got to zoom out here, guys. Sorry about that. I need to Okay, now actually let me go to the next problem. I should have another picture there. Okay, So what is the slope of the graph between points B and C? All right, so here's B, here's C. Okay, rise over run. So 1, 2, 3, 4, 5 over 1. So it's going to be decreasing 5 over 1. So the slope is negative 5. Oops, I gotta be careful here. I almost made a big error because I'm a dodo. This is very important that you see what your scale is in, right? This goes from 0 to 1. So the rise here is 1, and the run here is 1. So it's actually a slope of negative 1. Whew, almost made that mistake. So this is something for y'all to make sure you remember, is to take a look at your scale. Make sure you don't mess up that scale, all right? Like I just almost did. Write a complete sentence to explain the meaning of your answer in example 18. Well, what are we talking about? We're talking about the slope between B and C. So we're going to say the between 4 a.m. Oh, come on, erase. And 5 a.m. the rate of rainfall. Okay, we see a negative there, so I'm going to say decreases. Right? Another thing that you have to be careful with is when you ever use the word decrease or increase, you're talking about a slope. Okay, so the rate decreases, and what's the rate decreasing at? It's decreasing at a rate of 1. I believe this is in inches. 1 inch per hour per hour. Or 1 inch per hour per hour. Sometimes people say 1 inch per hour squared, but it's probably better to say 1 inch per hour per hour. Okay, so let's find the integral from 3 to 5. Okay, so that's the area that I already have highlighted here in red, in blue. I can't even. Okay, so we're just going to find this area that's in red. All right, we're going to do that just simply by taking the rectangle and the triangle that I have there. So the rectangle is a 1 by 1 rectangle. And the triangle there is a 1 by 1 by 1/2. So it's 1/2 base times height. And I'm going to end up with 1 and 1/2. Okay. Write a complete sentence and explain the meaning of your answer in example 20. So what does that mean? What does this integral mean? Remember, it's the accumulation between 3 and 5 a.m. So think about this. This was the rate of rainfall. So this is the rainfall. Rainfall. Okay, this is the rate of rainfall. Then what's underneath the curve is the accumulation of the rainfall. So between 3 a.m. and 5 a.m. The total rainfall was 1 and 1/2 inches. So it's accumulation of rainfall. Okay, so we're going to approximate the value from 0 to 6 of R of t. That's my function up there, using geometrical regions. So let me use green here. Or actually, let me use blue. So I'm going to do all of this. Okay, so I've got to estimate. So a good estimation would be to do maybe like, let me go ahead and just do this. Let's just do a rectangle or a triangle. I mean, that's an estimation, right? I mean, I know I missed these little areas, but this is going to take care of most of it. So that's going to be 3 by 1. So it's going to be 3 times 1 times 1/2 plus the red area that I got already. Okay, so that's going to be about 3. So what does that mean? Well, that means that the total rainfall from midnight to 6 a.m. was approximately 3 inches. All right. Now notice here that the 6 right here, this is flat, so there was no rainfall between 5 and 6 because it was 0. Okay, so there you go. So that's just an example of what I'm talking about in terms of looking at a rate graph and making it contextual. I think the key thing here for you guys to remember is that when you're doing the accumulation, okay, area under the curve, you're talking about the accumulated whatever context we're using. In this case, it was the rainfall. If we're talking about, I don't know, the amount of the rate at which we cut grass with a lawnmower, then if we have that, rate at which we cut grass on a lawnmower and we take the area under that curve, then we're talking about how much grass we cut with the lawnmower. So remember, it's just that whenever you take a rate graph and you find the accumulation or the area under that curve, that rate graph, you're talking about the total amount of stuff that you've collected or done. Okay? All right, guys. We'll see you next time. This is Mr. Myasis saying later.